Hello everyone, I'm Yaman Sanger, a graduate student in the University of Wisconsin at Madison. I'm working with Professor Bhuvana Krishnaswamy at the UW Connect lab, and I'll be presenting a demo of our work titled WiChronos today. In this work, we focus on the problem of scalability in low power wide area networks, also called as LPWANs. Consider a network deployed in a farm. So you have thousands of sensors that are deployed at distances ranging in the order of kilometers. Each of these sensors communicates to a central gateway. Now, these sensors are buried under the soil and deployed widely in large field, and replacing batteries is cumbersome. So these nodes must last for years. Now, these requirements of energy efficiency, long range, and large scale can be generalized to a majority of in situ monitoring applications, not just precision farming. And WiChronos solves the problem of the coexistence of these parameters. For most of the existing modulation techniques, the transmitted packet consists of a physical layer header followed by the payload. These header and data bits are all sent on the air, and the power consumption depends directly on their length. So the longer the message, the longer is the message duration, and hence more is the power consumption. We propose to encode data in the time difference between two symbols that we can call start and stop. Active data transmission happens in the time elapsed between these two messages. The transmitter module is maintained in deep sleep at that time, and so the power consumption is a constant depending only on the start and stop message, irrespective of the size of the payload. Thus, WiChronos separates the time on air from active transmission time. By choosing short anchor symbols and sleeping during the active transmission time, WiChronos reduces the energy consumption of the transmitter as well, so the time on air is entirely a function of these start and stop symbols. We calculated the battery life achievable for a small 250 milliampere hour 3.3 volt coin cell battery. WiChronos achieves a battery life of 10 years compared to LoRa, which goes to about 5-ish years, and Sigfox, which is less than a year. LoRa and Sigfox are state-of-the-art LPWANs that are commercially available right now. Whatever be the size of the payload, the battery life of WiChronos stays the same because the energy consumption depends only on these anchor symbols. Longer payloads reduce the battery life of the other method significantly. Let's also talk briefly about collision mitigation. Due to the simplicity of its implementation and its energy efficiency, Aloha is the most commonly used MAC protocol in LPWANs, but the collision performance of Aloha suffers with increasing network traffic. Now, collisions occur when one sender begins transmission during an ongoing transmission. So for instance, while sender 1 is transmitting its payload, sender 2 begins transmission while sender 1 wasn't done yet, and that causes a collision. So the data from both the senders is now lost, and since the headers and data occupy the channel for a long time, the probability of collision happening is high. When we take a look at WiChronos, sender 1 sends its start symbol whenever it's ready and then goes to sleep while data is actively being sent. Sender 2 uses the channel to send a start signal, goes to sleep, wakes up, and then sends a stop signal and completes its transmission. And eventually, sender 1 also transmits its stop symbol. The fact that these symbols are short and that the sleep time in between them is high in comparison, it is possible for them to be interleaved. So WiChronos is able to utilize the channel far more efficiently because of its lower time on air, and that reduces collisions. This is a plot of the collision probability of LoRa versus WiChronos for various network scales under various traffic loads. Due to hardware limitations, we could only conduct experiments for 12 transmitters, but on an average, the theoretical collision rate is 75% of the experimental rate. The theoretical results are an approximation for a large-scale network, and we expect the experimental results to match these theoretical ones for larger networks. But to recap, WiChronos operates on an ultra-narrow bandwidth for better signal-to-noise ratio and hence gives us an enhanced range. Short anchor symbols and active data transmission in sleep mode help in saving power. Reduced time on air and low data rate enhance the collision performance. Now, WiChronos leverages the relaxed data rate requirement of these monitoring applications to attain energy efficiency and reduce collisions. The following video demonstrates the same. We have emulated a LoRa transmitter, the one on the left, and a WiChronos transmitter, the one on the right, using MSP430 microcontrollers. Both of these are programmed to transmit 50 payloads of 2 bytes each continuously. LoRa has an 8-byte header along with a 2-byte payload, and all of this is transmitted over the air. WiChronos uses a start and stop symbol, each of 2 bytes, while the payload is encoded in the time difference in between them. The LED indicates the time for which the radio is on. We can see that LoRa is much faster compared to WiChronos in transmitting these 50 packets. However, the blinks for WiChronos are very short and amount to a total radio on time that is significantly shorter than LoRa. The radio is on for 60% less time when using WiChronos compared to LoRa. The radio is the bottleneck when it comes to energy consumption, and shorter time on air helps WiChronos achieve energy savings as well as reduce collisions. This next video shows a WiChronos transmitter and a WiChronos receiver. Our prototype uses the Lynx NT transceiver at a center frequency of 915 MHz and a transmit power of 13.5 dBm. MSP430 series from TI is the low power microcontroller that's used to control the Lynx device. The receiver is on the left and the transmitter is on the right. Now, each blink of the LED on the transmitter on the right indicates the transmission of a start and a stop symbol. When the receiver receives it, the LED on the receiver, which is on the left, blinks as well. The transmitter is programmed to send hexadecimal AA55 as the start or stop message. The receiver LED blinks only upon detection of this particular sequence, and the payloads being transmitted are an alternating sequence of 5,000 and 10,000. Now let's look at the received values next. So the raw data from the counter on the receiver that has been recorded has been displayed here. Note that the received data seems to differ by 276, 277, or 278 from the payload, and this is expected. We have presented a simple two-step error correction mechanism in the paper. First, subtracting a fixed value of 277, and then second, redundant mapping so that 4,999, 5,000, and 5,001 clock cycles are all mapped to a unique data value of 5,000. This way, each count on the receiver points to a single and specific payload value. The same funda is applicable for 10,000 as well. Please refer to the paper for more details on this. Raw values of data were chosen to be presented here to showcase the effectiveness of our error correction mechanisms and to show that the difference really is 277, 276, or 278. Now, while presenting range and concurrent devices is challenging here, I would like to talk about the energy consumption through some of the data that we have been able to capture. This plot has been taken from the Keysight multimeter used for current measurements, and each of these spikes represents the current drawn during the transmission of a start or a stop symbol. The transmitter was programmed to send a 2-byte payload every 5 seconds to obtain the graph that you see over here. Here is a zoomed in version of one of these spikes. Theoretically expected time period for which we expect the radio to be on matches the experimentally evaluated one from here. All the delay times that were programmed have also been evaluated experimentally in the very same way. Thank you for watching our demo. I am happy to answer any questions